Hi, in this video we'll show you a project we built using the SPI communication protocol. It uses a Raspberry Pi Pico W, a MAX7219 8x8 LED matrix, two servo motors, and an MPU 6050 accelerometer. The goal is to create a display that simulates a ball moving according to how the system is tilted.
Let's start with the hardware. The MPU 6050 measures the acceleration in 3 axes. It's connected to the Pico using I2C on pins 26 and 27. The LED matrix uses SPI communication and it's connected through MOSI pin 19. The SEK is in the pin 18 and the chip selected on the pin 21. The servos are powered with 5 volts and controlled using PWM signals from pins 16 and 17. One controls the pitch axis and the other the roll axis.
Okay, so we start by importing all the necessary modules. First we have the module math for calculations. In this line, we could also just import certain functions from this module, but we imported the complete module. We also have machine for hardware pins, for the I2C, the PWM, and the SPI communication. We also have the function sleep from the time module, as well as the custom libraries for the MPU 6050, the LED matrix, and the servos.
Okay. Now we initialize the accelerometer and wake it from sleep mode. Then we set up the LED matrix, selecting pin 21 for chip selected and set it in the radius level.
Next we have the servo setup. In here, the two servo objects are created using the library we talked about earlier, and each one starts at a neutral 90-degree position.
Then these two variables control the position of the ball that it's going to be seen in the LED display.
So now we're going to explain the rest of the functions that we included in our code, as well as the logic behind them. First, we need to read and understand the sensor data, the MPU sensor. The MPU 6050 gives us acceleration data in 3 axes, which are X, Y, and Z axes. This raw data doesn't tell us the orientation directly, so we need to calculate angles to understand how the system is tilted. With the function MPU.readAxleData, we get this information and we save it in the variables X, Y, and Z. Then we calculate the pitch and roll angles. Pitch is the forward-backward tilt, and it uses the x-axis, and roll is the left-right tilt, and it uses y and z-axis. So for this, we use the function addTan2 because it correctly handles positive and negative values, avoiding errors that are near 0 degrees. And finally, as we can see in the variables pitch and roll, we convert the angles from radians to degrees.
Now for the moving of the servos. Servos only accept angles between 0 degrees and 180 degrees. But pitch and roll range from minus 90 degrees to 90 degrees. So we shift and clip the values, adding 90 degrees. This lets the servos physically mimic the detect tilt in a real visual way. Now, on these functions, they work to move the servo shafts to the desired angle, causing the LED matrix to tilt in the same direction as the device.
Next, we have the functions that make possible the movement of the ball that is projected on the display. This logic is the heart of the quote-unquote ball simulation. Instead of moving a real ball, we draw it on the LED matrix, and we only move the ball if the angle goes beyond a limit of, or a threshold of about 10 degrees to prevent jittering or noise from moving it too fast. Also, we limit the position between 0 and 6 so the ball doesn't go off screen, because as it is a 2x2 square basically, we can only fit 6 of them in the LED display. So the roll controls left and right, which is the horizontal movement, and the pitch controls the up and down vertical movement. And this is what we included here in these conditions, what I just explained about the thresholds of about 10 degrees.
Now finally we have these functions that first it's gonna clear the screen, then we draw a 2x2 pixel square at the new calculated position. We use this and this, like this, to invert the direction of the movement. So tilting right moves the ball right, and tilting forward moves it downward, like in real life. Finally, the display show updates the matrix with the new ball position.
Okay, so why does all of this work well together? This is basically because this setup synchronizes 3 systems. First, the MPU 6050 senses how we're going to move the system. Then the servos tilt the actual physical matrix to match that orientation with the degrees that the MPU 6050 provides. And then the LED matrix shows a ball that responds to that tilt visually to the positions that we calculated with the if and elif conditions. The result is both a physical and a visual representation of orientation, which is a mix of hardware and software logic working in real time.
Now it's time to explain how libraries work. We're not going to explain the MPU 6051 because we already explained it in our last video. If you haven't checked it, go and watch it. Just to remember that this library wasn't made by us, it's by Team Henwich. It's the name says for the MPU 6050 accelerometer. Okay. Now let's break down how the custom servo class works behind the scenes. First, we import this library machine so we can use pin and PWM. Now, the constructor sets the pin as PWM and initializes the servo to a default angle. Servos expect a 50 Hz PWM frequency and the signal within in nanoseconds. This is what it's gonna define the angle. Now the next method, motion, change the position of the servo. It takes an angle 80 degrees and converts it to the correct pulse within. We have the stop method that, as the name says, it's gonna stop and disable the servo output. Now the conversion. This function performs how to convert the degrees to nanoseconds using a linear equation where 0 degrees is equal to 0.5 milliseconds and 180 degrees is equal to 2.5 milliseconds. This mapping is the standard for the servos we are using right now.
Okay, so now we're going to explain the MAX7219 library that we use for the LED matrix. This library provides an easy way to control one or even more 8x8 LED matrices using the MAX7219 driver through SPI communication, as we said earlier. It simplifies the low-level control of the chip and offers friendly functions to display text, to draw shapes, and even to adjust the brightness. Okay, so first, it's important to note that this library was not
written by us. It was made by Mike Kauser, but we're going to explain the features. First, the modules are imported. Const is used to define fixed values efficiently, and we import that from the MicroPython module. And also FrameBuff, which allows working with a byte buffer as a graphical display. Next, we have the command definitions. These constants are defined to represent commands recognized by the driver, such as shutdown, intensity, which allows to adjust LED brightness, display test that enables the test mode. So next we have the class initialization. In here, first, the code receives the SPI interface, chip select pin, and the number of cascaded matrices. It initializes a byte buffer to represent the pixels of all connected matrices, and it uses the function framebuff.framebuffer to easily draw on this buffer using built-in methods such as text, field rect, or pixel, as we can see down here. Rect is for drawing a rectangle, pixel is for turning on an individual LED, and text displays words with an already provided font. Then we have the function write, which sends data to the matrix. This method sends a specific command and data to each matrix via SPI communication, and handles communication for all the cascaded or joint units. The next function is the matrix setup. It initializes the display by sending a series of configuration commands, the ones we reviewed earlier. It turns off the display, then disables test mode. Then with scan limit, it enables the scanning of all the 8 rows, then disables decode mode, and finally it turns the display back on. And then we have the function brightness, which is for brightness control. It just adjusts LED brightness from 0 to 15, which is the maximum. And finally we have the show function, which is for displaying the buffer. It pushes the current content of the buffer to the physical display so all of the information can be shown by sending each row's data to every matrix. So this driver is efficient and it's flexible, and it supports multiple matrices, as we said earlier, allowing real-time animation and dynamic text with minimal code. To conclude our video, we want to say that this project shows how you can integrate sensor data, servo motion, and SPI displays to create a system that responds to real-world orientation in both physically and visual ways. It's a great example of combining I2C, PWM, and SPI communications in one real-time interactive application. So that's all. Thanks for watching.